Hello, here we are in lesson 2. We're going to look at power functions today. You're familiar with power functions. Any function that you can write in the form of y equals kx to the a power, where k and a are non-zero constants, those are called power functions. A is our constant, that's the power, and k is the constant of variation, or sometimes called the constant of proportion. When f of x varies as the ath power of x, we often say f of x is proportional to the ath power of x. Here's a few common formulas that you know from geometry and science, like the circumference is 2 pi r. 2 pi is our constant of variation, and the power on the radius, or our variable, is 1. Area for a circle, pi is the constant of variation, and the radius is squared, so the power is 2. Force is a constant divided by distance squared, so when we're dividing by a variable, that power is -2. Just as the same as in Boyle's gas law, the power on the pressure is -1, and k is our constant of variation. You also need to know how to identify when you have a formula like a half gt squared. So distance is a half gt squared. This is a broken down version of vertical motion. The power is 2, and our constant is half the gravity. Here we're going to take a statement like the area of an equilateral triangle varies directly as the square of the length s of its sides. You know, varies directly is an algebra term that you've seen often, like y equals kx. But we've got to convert that language to a for area and s for side. So the area as a function of the side is a constant, but my x is going to be converted to s for the square of the length of the side. So area of my equilateral triangle as a function of the side is a constant times the side squared. In this example, we want to be able to graph a power function. In this case, we have 2 to the 4th root of x. So our power is a 4th, and our constant is the 2. So we have a function that's growing quickly. It's going to be looking like a square root function. And if you think about the 4th root of 16, the 4th root of 16 is 2, so 2 times 2 is 4. And then if you think about 1, the 4th root of 1 is 1, and 2 times 1 is 2. So we have 1, 2, and 16, 4 as points of reference. And then they're asking us to analyze that function, so that's easy. You should be getting good at that. The domain is 0 to infinity. Our range is also 0 inclusive to infinity. Since 0, 0 is a minimum value, it's included in the graph. This function is increasing. It's continuous. It's concave down. And it's bounded below. It's concave down, bounded below, and a minimum value is 0. That would be an absolute minimum. Okay, so we pretty much analyzed that. Now let's think about some monomials for a second. Anytime you can write an equation like y equals a constant or y equals a variable times a constant to a power, These are called monomial functions. And whenever we have a monomial function and you have negative x values, three things can happen. Either the function is undefined for negative x's, and I'm going to give you an example. Say the square root of x, you know, that function has no values over here in quadrant 4. A function can be an even function, say y equals x to the 2/3 power, and that graph looks like kind of a bird flying in the air, x to the 2/3 power. So I do have negative values of x in this case. Or we could have an odd function like x to the 7/3 power. And the 7/3 power kind of looks like a cubic function. It's odd. It has origin symmetry. So we've got points in quadrant 1 and quadrant 3. So these are three things that can happen when you have a power function and you're thinking about x values. There's sometimes you'll have no negative x values, other times it'll have an even y-axis symmetry, and at other times, if it's an odd function, it'll have origin symmetry. And here, these graphs are graphs of what happens when you have a monomial function and either your x values are 0 or bigger than 0, so they're positive. And what I want to point out to you here, I'll give you some examples as we go along. So in this case, you notice that the ordered pair 1k is on the green, the red, and the blue graph. And over here in the second one, the same thing happens. 1k is on all three graphs. So the point 1k is on every graph. Every graph. Because we're going to talk about how these functions grow later on in the lesson. In this case over here, my k values are positive. And this is the behavior of what happens when the k values are positive. For example, on the green graph, if my k value was positive 1 and my graph was x to the 3/2 power. I'm sorry, that's the red one. Back that up. And my graph was x to the -1 power. Whoop. Go back to my pen here. If my graph was x to the -1 power, the graph would have a branch like this, so 1 over x. In the red graph, if the power was x to the 1.5 power, the behavior would look like this. And if the graph was the square root of x, the graph would behave concave down like we just saw on the 4th root. In this section over here to the right, this is when my k values are negative. So a few examples of that behavior would be, again, if this was negative x to the -1, the branch would be down here, where x to the -1 with a positive k looks like that. In the blue graph, let's make this square root negative square root. Whoop, not negative power though. Gotta watch me. And the red graph, same thing. I have x to the 3/2. I want to make that negative x to the 3/2. And then the behavior would go like this. So the k is positive. That k is my constant. I have positive 1k on all of these. the behavior of the graphs of the monomials are going to look like this. If I have negative k values, as all three are -1, -1, -1k, then the behavior of the graph looks like this. So we could summarize that by saying for the green graphs, the green one over here and the green one over here, the a value is less than 0, or the a value, which was the power, the a values are negative, and you get the behavior of the green graphs. The red graphs, the powers were positive, or I'm sorry, the powers were bigger than 1, 1.5, and the behavior looked like the two red graphs. And then the blue graphs, the powers were fraction powers, and you saw either concave down toward positive infinity or concave up towards negative infinity. Okay, so just some clues about how graphs behave on a monomial term. And like I said, we'll come back to that at the end. Here we're going to use the graph of x to the 6th and say what happens to the graph and sketch the graph. So we know that x to the 6th would be a very skinny parabolic looking function, but the -2 causes the graph to reflect across the x-axis. So it's going to reflect over x. And the 2, absolute value of 2, is going to cause the graph to stretch. So the stretch factor is 2, and it's going to stretch vertically, but it's going to stretch vertically in a downward fashion because we've reflected over the x-axis. And it passes through the origin. And we also know that the function is an even function. So we've got an even function. Okay, and if you wanted to, you could make a table and get some points to plot to see how rapidly it's going downward when you get to 2. 2 to the 6th power is 2x to the 6th is -128. So it's growing in a downward fashion very rapidly. This one is 3x to the 3rd. So we know 3x to the 3rd is just going to be an odd function, cubic, stretched by a factor of 3, growing rapidly. We know g of x is odd. And we know when x goes left, y goes down. And when x approaches positive infinity, y is approaching positive infinity. And name the leading coefficient. So our leading coefficient is 3. And in our next example, we want to talk about, again, I'm trying to tie the behavior of graphs. When you have large values of x, either positive or negative, some polynomials, say 2x squared plus 3x minus 5. At large values, I'm talking about very, very large values of x, we could consider that function by just considering the leading term or the largest powered term as the behavior for the graph. This is called an end behavior model for very large x's. And that whole idea or concept becomes important when we're looking at sequences and series in calculus. So we're just kind of exploring those possibilities. And here you can see for the extreme behavior, or just summarizing that end behavior, when x is heading to negative infinity, the y's are unbounded upward on both sides in either direction. But on an odd power function, when you go to negative infinity, y's go down. And as you head to positive infinity, y's are unbounded upward. For this even function, they both go down because the a value, or my constant, is negative, whether you're approaching negative or positive infinity. And in this case, it's also the opposite. When we head to negative infinity, y is heading up, and when we head to positive infinity, y is heading down. So just to summarize those things you know from previous classes. In this example, we want to be able to match 4 graphs. So we're using that last graph from example, which one was it? Right above example 4, with the 2 colored graphs with green, red, and blue functions. So when I have 3x to the 1/4 power, my power is 1/4, and my a value and my k value is 3. So that would be this graph A, that downward graph. And if you go back to that, you can see, use that as a reference. I can get back to it right here. So I've got this downward fashion right here. K is positive because K is 3, and my power is a fraction. So the fraction gives me that blue behavior. And number 2 is a negative, and it's an even function, so this would be C. Number 3 is a 2/3 power and a positive, so that would be letter B. And then by default, the negative would be to the 4/3 power. This would be D. Okay? In example 8, you're given the graph, and this one we just want you to analyze. The domain is negative infinity to infinity. You can see this is an even function. 4 divided by x to the 4th. It has y-axis symmetry. It's bounded below. There are no intercepts. Don't be fooled that these are intercepts. That's just hovering. That's a horizontal asymptote there. And then if you wanted to, you could also use our limit notation. The limit as x approaches negative infinity on that function f of x is heading to 0. And the limit to the right on the function is likewise heading to 0. That's how we know the function is bounded below. So here comes the relative rates of growth. We got to think about it. It's really important to understand that many functions go to infinity as x goes to infinity. They can go at different rates, fast or slow. So we want to look at 2 power functions and an exponential function first. In this case, we've got 2 to the x is the blue graph, x squared is the red graph, and the square root of x is the green graph. And what I see on the interval from 0 to 1 in this window is that f of x is bigger than the green square root of x, and then the square root is bigger than x squared, but that's just in this little interval. because when you go to the next interval, you notice that the square root is growing slower, and now the x squared parabola is growing faster. So we still have the exponential graph grows fastest, but now x squared is higher than the square root of x. And how can we determine what happens as you get really, really large? Well, a couple of things. If you knew about the limit properties from calculus, you could use those rules, but we're in pre-calc, so we can't really use those rules right away. We can compare y values, and you can use some algebra. So we can compare some y values for very large x values. And try to figure out what behavior is happening. But here's one really important note. Infinity is not a number, remember? It's not a real number. It's a behavior. So you got to consider that. We can't say we're plugging in infinity. And if you filled out this chart here, you'd get the square root of 2, which is about 1.4, and 1/4, and 1 over square root of 2. Here you got 2, 1, and 1. Here you got 16, 16, and 2. You notice how some of them are sharing points. And then behavior starts to go crazy. This one's 512, this one's 81, this is 3. At power 50, you got 1.12 times 10 to the 15th power. So that means 1, 1, 2, with 15 digits behind that decimal, 15 zeros. This one's 2500, this one's very small. So we're growing really slowly here. And then here again, 2 to the 100th power. Some of us might have a small calculator and it might crash your calculator, but you got 1.27 times 10 to the 30th power. This one you had 10,000. So 2 to the x is really, really growing fast. And if we put them in order of growth from smallest growth rate to the greatest growth rate, it would be k of x is smaller than x squared, and that's smaller than 2 to the x. So 2 to the x grows the fastest, k grows the slowest. So this is just kind of a little baby step as far as working our way through pre-calc to understand some of the more difficult concepts in calculus. Here's an example of that theorem when I said for very large values of x, you can think about which grows faster by just ignoring the end of that trinomial. All you have to really think about for super large numbers as x approaches infinity is to know that x cubed is bigger than x squared. So this graph, this function grows much faster than the parabola. In this case, x cubed is bigger than x squared, but I also have an exponential function, sort of like 2 to the x power. E to the x is going to grow way faster than this, so I could ignore this part and think about e to the x, or I could also consider that together the sum of them is going to grow much faster than x cubed. And we saw that with the table. So we have this one growing much faster than x cubed. And like I said, the reason basically is the piece that's e to the x is going to way surpass x to the third. And here you got to think about it. How big is e? Well, E is about 2.718. And how big is pi? 3.14. So which one is going to grow faster? E to the x or pi to the x? It's going to be pi to the x. Okay, here comes our last example. So in this case, it's important to see that relative growth rates will be helpful in future courses. And here's 4 things that are important. Any 2 polynomial functions of equal degree grow at the same rate. I'm going to put a little remark here. So for example, if I had a function like x to the third, and I also had a function like 2x to the third minus 5x squared plus 7. Remember, I'm only considering these 2. And the statement says any 2 polynomial functions of equal degree grow at the same rate. That means if you consider x cubed and 2x cubed, even this factor of 2 for very large x's are still going to grow at the same rate. And like I said, if I knew the rules about limits, I could use those. But we don't know the rules about limits yet. And one thing you could do is you could think about comparing them as a ratio. And if you thought about x cubed divided by itself as a form of 1, and your result was either 2 or 1/2, that's the ticket to the idea about using the properties of limits. That's why they grow at the same rate. So, yep, we're not teaching calculus. We won't get into all of that can of worms, but just so you know. And it's coming. And the second important feature is if you have x to a power, it's going to grow slower than x to a different power if the power on this one is less than the power on the second one. So we could say something like x to the 7th and x to the 12th. 7 is less than 12. So this one, x to the 7th, is growing slower than x to the 12th. And it works in reverse too. That's a biconditional. And a to the x, we just saw that with our e to the x and pi to the x right here. We just saw that. So if your base of 1 is smaller than your base of another, then the base that's the smallest grows slower than the base that's the bigger. So 2.7 grows slower than 3.14 to any exponential power. The same thing with 2 to the x is going to grow slower than 7 to the x, right? So let's see about these 2. We got 2 more to go. Consider the functions 4x squared and x squared plus 5x minus 2 for sufficiently large positive values of x. We know the end behavior of the graph of g is positive infinity, and it's going to resemble x squared from the theorem that we had right in example 6. So if we compare the ratio of the 2 functions for these large values, like I said, if I compared f of x to g of x, f of x for large values behaves like 4x squared, and g of x for large values is going to resemble x squared. When these are the same, you could algebraically think of removing that, and when I got a constant number like that, I got a constant, a finite answer, then I know no matter what the multiplier, that f and g grow at the same rate. So we can say that in a sentence here. Grow at the same rate. You notice I haven't taken a calculator out because I'm going to get confused using a calculator and plugging numbers in. Our calculators are not able to handle the large values of x that we need. We just need to think about properties in these cases and the rules that we have. Okay? And then last example, I'm going to kind of do the same thing. Use the properties of exponents and compare the ratio. So if I compare the ratio of f of x to g of x, you know, we could use the rule. What was it? Rule number 3 said if 2 to the x and e to the x, depending on the bases, this base is 2.718 roughly. So 2 has to grow smaller than e to the x because the base is bigger. We know that this one is the faster growing, but I want to show you how you could mathematically think about this. So I've got 2 to the x divided by e to the x. Algebraically, I could say since they're both to the x power, I could think about this as, I've already pre-done this, I'm sorry. 2 divided by e is about 3/4. So if you think about it, if you had 3/4 raised to some huge number, you're going to basically go to 0. So as x gets bigger, the ratio is approaching 0. And that's the limits or the calculus way of thinking about rule number 3. This was rule number 3. Rule number 3 said that 2 to the x is slower than e to the x because the bases were bigger, because the base of e is bigger than the base of 2, right? So don't get too taken up with me just kind of exploring and thinking ahead to calculus, because you're not going to be tested on that in pre-calc, but just the fact that those rules hold and why they hold, I just wanted you to see that little extra bit. So these rules hold, and that's the kind of stuff you need to know for pre-calc. I'll see you in lesson 3. Bye.